Hello everyone. In the previous class we have discussed about the system tasks in which we have covered display, monitoring, stop and finish tasks. So in today's class we will cover first compiler directives. So compiler directives are provided in Verilog HDL language. So all compiler directives are defined by using the keyword tick keyword tick followed by backtick followed by a keyword construct. So see here how is the compiler directive is going to be used. The tick mark and the corresponding keyword is going to be used. So we deal with the two most useful compiler directives. The first one is the tick define. I hope you have studied the C programming in which we have come across hash define. The hash define is a macro in C programming. So similar to that one, here the function of the tick define is same as the hash define in C programming, but the only construct or syntax used here is tick define. So the tick define directive is used to define the text macros in Verilog. The Verilog compiler substitutes the text of the macro whenever it encounters a tick macro name. So that means whenever we use any word or any text with a tick define compiler directive, it replaces its value in your program. So it is going to substitute that text macro with the declared value. So this is similar to the hash define construct in C programming. The defined constant or text macros are used in the Verilog code by preceding them with a backtick. So see here the example for tick define directive. Define a text macro that defines default word size used as word size in the code. Tick define word size 32. So in your program, whenever you write your program, suppose if you use a tick define and any name, here the name used is word size and 32 is declared for that particular text word size. So whenever the same pattern of text appears in your program, that is word size, that word size is going to be substituted with the value 32 in your program. So that is the function of the compiler directive. So what is the use of this one? Suppose if you are writing the program, your program is very large. In that case, you are using this word size, for example, many number of times. That is the value 32 as an example, you are using that one many number of times. Suppose if you are doing a trial and error method, and if you want to change that number from 32 to any other number, so if you are not using a tick define, then what happens? Every instance in the program has to be replaced with that particular value 32. Suppose if you are using that 32 10 number of times in your program, so all the 10 times you have to change that value from 32 to any other number if you are not using tick define. But if you use this macro tick define, and if you have declared that 32 as a using some text, for example here word size, then only you need to change the value once here while the declaring, that is tick define while word size from 32 to any other number. So if you do this, every instance in your program is going to be substituted whenever it is compiled. That is, compiled directive is going to substitute the new value with the old value. So your effort of searching all the values and replacing that value with a new value is going to be denied here. That's why it is better to use the macro in your program. So the first example is tick define word size 32. Second example is define an alias. A stop will be substituted whenever yes appears. Suppose if you want to use suspend your program many number of times, so say some 20 times in your program, so instead of writing the compiler, instead of writing the system task $stop every time, replace that with some text. That is, here in this case it is yes. So if you use yes, just yes in your program whenever you want to suspend your program, then just by declaring tick define yes $stop, and you whenever that system task has to be used, just write yes, so that it is going to be replaced with the substituted with the $stop. So system task will be executed. So this is the easiest method. Define a frequently used text string. That is, example, tick define word reg 31 down to 0. So similarly, if you want to use reg 31 down to 0 many number of times, instead of declaring it again and again, just use a tick define word reg 31 down to 0. So n number of times that will be replaced in your program. You can then define a 32-bit register as word reg 32. The second one is the tick include. The tick include directive allows you to include entire content of a Verilog source file in another Verilog file during a compilation. So this is again same as the hash include in your C programming language. So whatever the hash include function does, the same thing is done by the tick include in Verilog. So what it is going to do, it is a directive that allows you to include the entire file, the complete file, that particular file of a Verilog source file in another Verilog file during the compilation. Suppose if you want to use an entire file which is with another name followed by the extension of Verilog HDL, then if you use that file name using tick include in this program, then the complete source file will be included. The content of that particular source file will be included in your new file. So this works similarly to the hash include in the C programming language. So this directive is typically used to include header files which typically contain global or commonly used definitions. So what is the purpose of using this tick include? So this is typically used to include header files. You know header files in C programming, that is stdio.h, hash include stdio.h. stdio. is a header file. Similarly here also you can create your files which can be used as a header files in your another file. So that how to include that one? By using a tick include, so which typically contains some global or commonly used definitions. Example for tick include directive. So include the file header.v which contains declaration in the main Verilog file design.v. So see, suppose you have a main Verilog file which is called as design.v, in which you want to use header.v file. .v is the extension for Verilog HDL program. Then tick include header.v, so that program is there. Then Verilog code, this tick include header file, header.v is going to be used in your design.v file. All the content of the header.v will be used in design.v file. So design.v is the main file, header.v is another file which is going to be used. It's all the contents will be used in design.v file. How to use this? By using a tick include. Next part, modules and ports. So in the previous chapter we have already discussed about the fundamentals of hierarchical modeling concepts, basic conventions and Verilog constructs. So here we are going to take a closer look at the modules and ports from the Verilog point of view. So in detail we are going to discuss the modules and ports with examples. So this is very important part for writing the programs. For start writing the programs, first you need to study or understand the constructs or keywords or the syntaxes, then only the logical part will come. So we discussed how a module is a basic building block in first chapter in hierarchical modeling concepts. We ignored the internals of the modules and concentrated on how modules are defined and instantiated. So just we came to know that there is a module which is a basic building block in the first module, but we have ignored the internal part of the module. How to write that internal part, what are the internal parts, etc., that we do not know yet. So in this module we come to know that what are the internal parts of the module. Then in the from the later third module we will going to see how to write the internal part of the module. So in this part what we are going to discuss, what are the different components of the modules that we are going to discuss. Then how to write those components will be discussed in the module number 3. So in this section we are going to analyze the internals of the module and module in greater detail. So this figure shows the components of a Verilog module. Observe the figure very carefully. This is very important. So in the first block we have a module name, port list, port declarations. If there are any ports, then only the port declarations will come. Then parameter list. So parameter list is optional. If you have any parameters need to be declared, then only it can be used. Then in the second block we have 5 different components. So these are the internals of the modules. We do not know about this yet. So we are doing this first time. So in the internals of the module we have declarations of wires, reg and other variables. That is declaration part. What are we are going to declare? Different wires, if there are wires, registers, if there are registers, then any other variables if they are required for that particular program. Then we have different type of modeling concepts. So based on those concepts, whichever modeling concepts that you are using in your program, those according to those modeling concepts the syntax and semantics will come. So for example, data flow statements, the assign is the keyword. Then instantiation of lower level modules. So this is a gate level modeling or structural modeling. Then always and initial blocks, that is all the behavioral statements are going to come in this block. Then if you have any tasks and functions, those are going to be used. So all these are internals. So here data flow modeling or structural modeling or behavioral modeling, all these are separately used. Any one of those will be used or mixed in any order it can be used. So it is not compulsory that you have to use particular modeling itself. So based on the design based on the question asked in the exam, etc. You can use any module in the as the internal. So here all the internals whichever is are possible, that is shown here. So you can use either one internal, one modeling concept, two modeling concept, or all the three mix modeling concepts in any order. It is not mandatory that data flow modeling has to be at the first, behavioral modeling or structural modeling. So any order you can write. Tasks and functions, if it is necessary, then you can include those also in your module internals. Then at the end module statement, it is compulsory. So a module definition always begins with the keyword module. A module definition always begins with the keyword module. Remember here, module, M-O-D-U-L-E, module is a keyword, all the small case letters. So this is your keyword, followed by the module name. Module name is given by the user. It is a identifier as per your requirement of the program. Any name will be provided using the identifiers rules. So the module name, port list, port declarations, and optional parameters must come first in the definition. So after the module name will come, and if there are any ports, those port list and port declarations you have to write. Then if there are any parameters, those can be included. So all these are going to be come first in the module definition. So next, in the middle, that is the internals of the module, port list and port declarations are going to present only if module has any ports to interact with the external environment. Ports are nothing but the IC pins. So you have different type of pins, input pins, output pins, or IO pins. Both the same pin can be acting as a input or output. So such pins, if they are required in your design, then you can declare the port list. So the 5 different components within a module are variable, declarations, data flow statement, instantiation of a lower module, behavioral block, and tasks or functions. Just now we have discussed. So out of these 5 type of components, any one or all of them are required as per the design or requirement of the designer or the program. So these components can be in any order or at any place in the module definition. The end module statement must always come last in a module definition. Remember here, end module without any space between end and module, continuous end module with the small case letters must be the last statement in the program. All components except module, module name, and end module are optional. So see here, all the components that we have discussed as the internals of the module, so except module followed by module name and the end component, end module. So these are essential for every program. All the other things are optional. So all components except module, module name, and end module are optional and can be mixed and matched as per the design needs. So module and module name is compulsory and end module is compulsory. Remaining all the things are optional. If they are required in a program, then only you can include them, otherwise you just skip it. So Verilog allows multiple modules to be defined in a single file. So remember here, Verilog HDL programming allows the multiple modules to be defined in a single file. So read this carefully. Multiple modules to be defined in a single module. That does not mean module within module is possible. Module within module is not possible. Nesting of module is not possible. But within a single file, many number of modules can be possible. So once the module starts, it must end the module. Then only you can start the new module in a same source file. The meaning of the Verilog allows multiple modules to be defined in a single file is. the modules can be defined in any order in the file. So if you are using some 3 or 4 modules, so you can define those modules in any order. There is no need of whichever the module that first runs, that has to be first. So any order you can use. Example, so observe the figure carefully. So this is a SR latch. So SR latch consists of 2 NAND gates, N1, and the down one is N2. The name given here is N1 itself, but make a correction. The above NAND gate is N1, the below NAND gate is N2. It has 4 ports, 2 input ports, 2 output ports. S bar and R bar are the input ports, Q and Q bar are the output ports. And the cross connection from the Q to N1 input and Q bar to Q to N2 input and Q bar to N1 input. So this is the figure of SR latch. So the SR latch has S and R as the input port and Q bar as the output port. So how the module is used? Here this program just discussed because to understand how the module internals are going to be used. How to write the program, that will be discussed in the module number 3. Here just observe how the wires, registers or any other variables can be declared, how the instantiation of lower level modules can be done by using a gate level modeling or structural modeling. So here this example illustrate the different components of a module. So different components, that 5 different components, out of that few components are used, not all the 5, few components are used here. Module name and port list, SR latch module. So see here, MODULE, module is a keyword, that is start of the program. Module is a keyword, SR latch is a module name. As we are doing the SR latch example, so we have used the name SR latch. This is user defined name, any identifier it is. So you can use SR L or any other thing that you want. Then list of ports, Q bar, S bar, R bar are the port list, followed by bracket and termination, semicolon. Then port declaration. So out of Q bar, S bar, R bar, which is input and which is output, that has to be declared. So that is called as port declaration. So output is a keyword here. Output, Q and Q bar. Q and Q bar are the outputs. You can observe the figure and you can decide which is input, which is output. Output Q bar, and input is a keyword INPUT. So output and input all are keywords in a small case letter. S bar, R bar are the inputs. Now the programming is done using a gate level modeling or structural modeling. This is just an example. You will understand this part in the module number 3. So instantiate lower level modules. In this case, instantiate Verilog primitive and primitive NAND gates. Note how the wires are connected in a cross coupled fashion. Just observe the figure here. NAND, NAND, NAND is a keyword here. N1 is the instance. So N1 is given in the figure. It is that particular NAND gate. Suppose if you have n number of NAND gates, similar gates, all the gates will be given some name. So those names are nothing but instances. Instances are optional in program. You can skip them. Here N1 is the instance that we are using. For that NAND gate, we have a Q output, S bar input and Q bar input. So we have 2 input and 1 output. Out of that, Q is the output and one is S bar, which is direct input, and another one is the Q bar, which is cross coupled. Output is taken as an input here. So Q, S bar and Q bar is the instantiation part. Then NAND N2, second NAND gate, its instance is N2. Correction in the figure, the below NAND gate is N2. Same name of instance is not used. So N2, so observe the figure for the NAND gate 2, N2, the Q bar is the output, R bar is the input, and one more input is from Q. So that's why NAND N2 Q bar, comma R bar, comma Q. This is the instantiation. Then end module statement. So final statement in any module is end module. So observe here, out of that 5 components, we have used only the instantiation of lower level module and some declaration part. Other data flow modeling, always or initial block, and task functions we have skipped. Only one type of modeling and the declaration part we have used. Then second module here, that is module name and port list stimulus module. This is stimulus module is nothing but a test bench. How to write a test bench, that will be discussed later in the module number 3 or later. So name of the module is top, module top. So declaration of wires, reg, and other variables. See here, wire is a keyword, Q bar, but whichever are the output, that has to be declared as a wire in a test bench or stimulus. Then inputs can be declared as reg, set, reset. So instantiate lower level module. In this case, instantiation of SR latch, feed inverted set and reset signals to the SR latch. So SR latch M1 is the instance name. Complete SR latch is taken as one block. Q bar, not of set, not of reset, that is tidal sign. So what all this, that will be discussed later. Behavioral block initial, this is a behavioral statement. Then initial keyword, it is keyword. Begin is grouping. Begin monitor function, $monitor, $time, that is current simulation time it is going to give. Set is equal to %b, reset equal to %b, q is equal to %b /n, set reset q. So we have discussed the monitor function. So this is used to monitor any one of the value changes, then it will display that particular values on the screen. So what all different values here, that is current simulation time, then set value, reset value, and q in all the values are in binary. /n is used to go to the next line. So set equal to 0, reset equal to 0. After 5 time units, reset becomes 1. After 5 time units, again reset becomes 0. After another 5 time units, reset becomes 1. End module. So this is just an example. So notice here that the following characteristics about the module defined above. In the SR latch definition above, notice that all the components described in figure need not to be present in a module. So it is not mandatory that whatever the figure that we have, everything may not be present in your module. We do not find variable declaration, data flow, that is assign statement, or behavioral block, that is always or initial. So as we already told that components of a Verilog module figure, we have so many things, 5 different components. All the 5 components are not compulsory parts of your module. Any part that is required or designer interested, then only you can use those blocks in your program. However, the stimulus block for the SR latch contains module name, wire, reg, and variable declarations. Instantiation of lower level modules, behavioral block, that is initial, and end module statement, but does not contain port list, port declaration, data flow, that is assign statement. Observe the stimulus block, which consists of again few parts, which does not consist of few parts. So all are optional here. Therefore all the parts except module, module name, and end module are going to be optional and can be mixed and matched as per design needs. So that's why we have taken this as an example. So Next part we are going to discuss it in the next class. Thank you for watching the video.